Hello and welcome. Today we are going to explore the specialized architecture of AI factories. We will move beyond traditional data center concepts to understand how scalable units, rail-optimized topologies, and advanced acceleration components like DPUs and Super NICs create the foundation for generative AI. Let's begin by defining our environment. You might be used to general-purpose clouds, but AI requires a different approach known as the AI factory. In these environments, we aren't just hosting web servers. We are training trillion-parameter models that require massive distributed computing power. The network here isn't just plumbing. It effectively defines the data center's performance. If your network has high tail latency, your entire training job slows down to the speed of the slowest node. What did we learn? We learned that AI workloads demand a specialized infrastructure where the network is integral to compute performance. The important point is that in an AI factory, the network determines the efficiency of the entire supercomputer. This diagram contrasts the two environments. On the left, we see the traditional data center. It handles loosely coupled workloads where basic connectivity is sufficient. Now, look to the right at the AI factory. Here, workloads are tightly coupled. This means thousands of GPUs must act as one computer. To achieve this, we cannot use standard networking. We need high-performance, lossless fabrics like InfiniBand or NVIDIA Spectrum-X to handle the distributed training requirements. This visual shift represents the fundamental design change required for the era of AI. Now, let's look at how we construct this factory. We don't just rack servers randomly. We build using scalable units or SUs. Think of an SU as a Lego brick for supercomputing. For example, in a DGX superbody, an SU might consist of 32 DGX systems. By designing in these blocks, we ensure that the network topology within the block, the compute fabric, is optimized for maximum bandwidth before we even connect to the larger data center spine. This modularity allows us to predict power, cooling, and cabling needs accurately. What did we learn? We learned that modular SUs are the foundation of scalable AI clusters. The important point is that SUs allow organizations to scale linearly without hitting unexpected network bottlenecks. This visual represents a single scalable unit. Inside the box, you see the compute nodes, such as DGX systems. These are tightly connected to their local leaf switches. Notice how the SU encapsulates this complexity. The connections going out to the spine switches allow this single unit to connect with other SUs. This modular approach simplifies the massive complexity of wiring thousands of GPUs. Within that scalable unit, we use a specific cabling strategy called rail-optimized topology. In traditional networking, any server port connects to any switch port. In an AI factory, we are more precise. We connect the first GPU of every server to the same specific switch, forming Rail 1. We do the same for the second GPU to form Rail 2, and so on. Why? Because during AI training, GPU 1 often needs to talk to GPU 1 on other nodes. This topology creates parallel, non-blocking highways for data, drastically reducing the number of hops and latency. What did we learn? We learned that cabling isn't arbitrary. It follows the GPU architecture. The important point is that rail optimization aligns physical cabling with AI communication patterns to maximize throughput. Here is the rail-optimized concept visualized. On the left, we have node A, and on the right, node B. Notice that GPU 1 from both nodes connects exclusively to the top switch, labeled switch rail 1. Similarly, GPU 2 connects only to switch rail 2. This ensures that when GPU 1 needs to broadcast data to its peers, it has a direct, dedicated lane without competing with traffic from GPU 2. This structure is essential for deep learning communication primitives. For the highest performance, we look to NVIDIA Quantum InfiniBand. It's not just moving data, it's processing it. This is called in-network computing. A key feature here is SHARP. In traditional networks, data goes back and forth between nodes to be averaged or summed. With SHARP, the switches themselves perform these calculations as the data passes through. This effectively doubles the data bandwidth available for these operations. Furthermore, adaptive routing ensures that if one path is busy, packets instantly take an alternative route. What did we learn? We learned that smart switches can process data, not just forward it. The important point is that offloading collective operations to the switch via SHARP significantly reduces training time. This diagram illustrates SHARP in action. Data leaves node 1 and node 2 and enters the quantum switch. Instead of the switch just passing packets between them, look at the orange box. The switch performs the reduction calculation internally. It then sends only the final result back to the nodes. This reduces network traffic congestion significantly compared to traditional methods where nodes must exchange data multiple times. While InfiniBand is powerful, many cloud providers prefer Ethernet. However, traditional Ethernet is lossy and slow for AI. Enter NVIDIA Spectrum-X. This platform tunes Ethernet for AI by combining Spectrum 4 switches with Bluefield 3 DPUs. It introduces lossless Ethernet capabilities, ensuring data isn't dropped during transmission. It also implements ROSI adaptive routing, which sprays packets across all available paths to avoid congestion, reordering them at the destination. This is crucial for multi-tenant clouds where you need performance isolation. What did we learn? We learned that Ethernet can be optimized for AI to rival InfiniBand performance. The important point is that Spectrum-X resolves traditional Ethernet's packet loss and jitter issues for AI workloads. This sequence diagram shows Spectrum-X adaptive routing. The source DPU sprays packets across different paths to the switch to maximize bandwidth usage. The switch forwards them and they may arrive at the destination DPU out of order. Crucially, notice the note on the right, the Bluefield 3 DPU reorders these packets in hardware before handing them to the application. This allows the network to be fully utilized without confusing the application. A critical component in the AI factory is the endpoint. We use NVIDIA Bluefield-AIN DPUs and Super NICs here. The DPU acts as a computer in front of a computer, handling security and storage tasks, so the GPU can focus entirely on AI. The Super NIC is a specialized version designed specifically for AI clouds, capable of 400 speeds. It works with the switch to enforce congestion control, ensuring that one heavy user doesn't slow down everyone else, a problem known as the noisy neighbor. What did we learn? We learned that the endpoint is as smart as the switch. The important point is that DPUs and Super NICs isolate infrastructure noise, preserving GPU cycles for training. Here we see the architecture of a node equipped with a Bluefield 3 DPU. The host CPU and GPU connect via PCIe to the DPU. The diagram shows the DPU splitting tasks. It handles security and storage locally, offloaded tasks, preventing that load from hitting the host. Simultaneously, it manages the high-speed AI traffic to the network. This separation is key to efficient and secure multi-tenancy. To move data fast enough for AI, we cannot use standard TCP/IP processing, which burdens the CPU. We use RDMA, Remote Direct Memory Access. Even better, we use GPU Direct RDMA. This technology allows a GPU to talk directly to the network interface card, NIC, and then to a remote GPU, completely bypassing the host CPU and system memory. This creates a direct fast lane for data, drastically lowering latency. Without this, the CPU would become a bottleneck, unable to feed the GPU's data fast enough. What did we learn? We learned that the CPU is a bottleneck we must avoid. The important point is that GPU Direct RDMA creates a direct path for data between GPUs across the network. This flowchart visualizes the data path. Data moves from GPU memory on node A directly to the NIC, crosses the RDMA fabric, and enters the NIC and GPU memory on node B. Notice the CPU node with the dotted line? It is bypassed. In a non-optimized system, data would have to go up to the CPU and system RAM before hitting the NIC, adding significant delay. GPU Direct removes those steps. Finally, designing the network is one thing, operating it is another. For InfiniBand, we use UFM, Unified Fabric Manager, to manage the subnet and monitor health. For Ethernet, we use NVIDIA NetQ. A critical feature here is WJH, or what just happened. If a packet is dropped, WJH tells you exactly why, whether it was a buffer overflow or an ACL deny, and gives you the context to fix it immediately. This visibility is mandatory for maintaining the high availability required by AI factories. What did we learn? We learned that visibility is as important as bandwidth. The important point is that advanced telemetry tools like UFM and NetQ are necessary to diagnose complex congestion issues in AI networks. The final diagram shows the telemetry pipeline. The network switch generates raw telemetry and WJH data. This is picked up by the NetQ agent or sent to the UFM platform. This data is processed and presented to the network admin on a dashboard. This loop allows the administrator to see real-time issues, rather than waiting for user complaints about slow training jobs.